This is another example of a two-level predictor with local history. So we have the PC here. Some bits of the PC are going to be used uh, to concatenate with the branch history table entry. And some bits of the PC are also going to be indexed into the BHT. So this concatenated entry is now going to be used as an index into the pattern history table. And finally, the entry here, which is a two-bit predictor or a two-bit counter, is used as the final decision for the branch. So if you also look at the other diagram, so this is just showing what happens in the next iteration. So now having taken this as the branch decision in the first iteration, so one is taken and let's say zero is not taken, then all we do is we're going to shift this left and then make that entry the new entry, which is the taken entry here. So basically the history bits are going to change. 1010 is going to be left shifted, so it's going to become 0101. This one is coming from the fact that this decision was a taken decision, and then that is going to now used to index. You're going to concatenate it with the PC and then index into another entry here, and this is going to be the new decision. So this is the not taken decision. So this is how the two-level predictor works. And if you have an n-bit history predictor, then we know that the n-bit history predictor will predict patterns correctly for length which is less than or equal to n plus 1. So what is the cost of this predictor? So it is going to have an n-bit history, and in addition to the n-bit history, the n is going to index into 2 power n counters, and each of this counter can be m bit wide. So we have the history bits plus 2 power n multiplied by m bits. So for example, if you have a 1-bit counter with a 2-bit history, so you have the 2 bits for the history, and it's going to index into 4 counters, each of them 1 bit wide, and therefore you have 6 uh, bits per branch entry. So obviously, if a pattern does not occur, those bits get wasted. So like I said, although we have 2 power n counters, there might be only some patterns which are used. And if it's an n-bit history, we're going to use only up to n plus 1 counters. The rest of them are wasted. So the other idea is, instead of wasting these many counters, we can share these counters between different branch entries. And another comparison is the size of the BHT and the PHT. So for a given size of the pattern history table, if you increase the branch history bits, then what is going to happen is it is going to be useful. So it's going to be useful to increase or have larger history of branches, because if you increase the history bits, you can relate to more previous occurrences of the branch. But then what is also going to happen is, let us go back to this slide. So if you increase the number of history bits, then the number of bits that you're going to take from the PC are going to reduce, because let's say in this case you need 6 bits to index into PHT. So let's say I increase this to 5 bits. So then the BHT entry is going to be 5 bits, and I'm going to take only 1 bit from the PC. So this is going to be a disadvantage because there are going to be more collision, because there might be more branches which map to the same PC bits. So this is another useful thing to keep in mind. So like I said, um, there are there is an idea here that we can share this counters between different branch entries so that we do not waste the counters. So that is the idea behind global history predictors. So whatever we discussed so far are just local history predictors, because they are going to keep track of the history of the same branch and not other branches. And global history predictors keep track of other branches as well. One of the examples is what is called a correlated branch prediction. You can also call this global branch prediction or global history predictors and so on. So it's also called correlated branch prediction. So what this means is, let's say we have 3 if conditions. If A equals 2, then make A 0. If B equals 1, make B 0. And if A is not equal to B, then we execute something else. Now we see that this branch B3 is related to the outcomes of B2 and B1. So for example, if A equals 2, then A becomes 0. And if B equals 1, B becomes 0. So A and B are equal, and therefore if this if condition is not going to be met, and therefore it is going to execute something else. Whereas if this was true, then this is going to go in a different path. So basically this branch is related to the occurrences and to the outcomes of the two previous branches. So similarly, this is another example. If A is equal to 0, then make A equals 1. And if A is equal to 1, execute something else. So therefore, you can see that there is another example here also. You can go through this. So basically, a branch's outcome or a decision can be related to not just that previous occurrence of that current branch, but also to the outcomes of previous branches. So if you want to figure out the outcome of B3, it is good enough to know the outcomes of B1 and B2. So this is what is called correlated branch prediction. So basically this predictor combines the local behavior of that branch along with global information of other branches, other executed branches. So this is usually depicted as M, N predictor. M means how many branches are we going to keep track of. So in the previous case, we kept track of B1 and B2. So two previous branches. So here M is going to be 2 because we want to keep track of the last M branches. So if we have M branches, then obviously there's going to be 2 power M history tables. So for each branch, we're going to keep a table, a history table, to keep track of its previous outcome. And each of them can have n bit counters. So it could be a 1 bit counter which just has taken, not taken decision, or it could be a 2 bit counter with the 4 states: weakly not taken, strongly not taken, weakly taken, and strongly taken. So it could be any of those n bit counters for each of those predictors. So, for example, what we have seen initially, this 2 bit counter that we saw initially, or 2 bit predictor, is a 0, 2 predictor. The 0 means that it does not keep track of any previous branch. So it just keeps track of the current branch. Therefore, this is 0, 2, or it doesn't have any history. A 2, 1 predictor is a predictor which keeps track of the last two branches. It uses the behavior of the last two branches to choose from 2 power 2 or 4 different predictions. And it uses a 1 bit predictor, that is just a taken or a not taken predictor for each of the 4 prediction buffers. Okay, so the way this works is let us say, for example, we're not going to use any PC bits at all. This is one way of implementing it. So we just have one global history buffer, or BHR. So instead of a branch history table, we're just going to have a branch history register. And this is a global history register, which means that we are not keeping track of any a specific branch. We are not keeping track of any specific branch, but we keep track of different branches. So if the outcome of this particular branch is taken, we update it here, and the next one is updated here. So basically, it is going to just keep shifting left according to the outcomes of the branches. So then this is going to index into a pattern history table, and you're going to choose this outcome. And this may not be the best way, because as and when you get more branches, you're going to keep shifting the contents here, and therefore it may not be really the best way of doing it. So the more popular one is this global history predictor, which uses the PC bits. This is also called the Gselect branch predictor. You can also refer to this particular video for more information. So as I mentioned earlier, global history predictors do not have branch history tables. So because branch history tables are specific to a particular branch, uh, because they usually keep track of a particular branch's history. Um, and since we are keeping track of global history here, we have a single BHR. So that is, sorry, that is not the BHR. This is the BHR. So this is usually a good way of differentiating between whether this is a global predictor or a local predictor. So global predictors usually have just the BHRs, whereas the local predictors have the branch history tables. So now here we are using the PC bits. Some bits of the PC are going to be used and concatenated with the branch history register. So this branch history register is going to keep track of four different uh, branches. It need not be four different branches. It could also be the four previous occurrences of branches. So if you have B1 and B2, and again B1 and B2 is repeated, this could be just the outcomes of these in that order. So we now concatenate this, and then we're going to index that into the PhD. So basically what I've written here is PC will not index into the branch history table because it doesn't exist. So we're going to have a single BHR, and we're going to consider the n most recently executed branches. It could be same or different. And any branch's outcome is updated in this BHR. And finally, you take this outcome as the prediction of that branch. So this is another way of viewing it. Some books or some papers may also view it this way. You can divide the PhD uh, into different sets or components. So if you have two bits from the PC, we can think of it as, for example, this is indexing into 0, 0. If the PC was 0, 0, it will index into the first part of the PhD. 0, 1 will index into this part, 1, 0, and 1, 1. And inside each of this component, this BHR, which is basically concatenated with the PC, can be viewed as an offset. So if you consider this particular concatenated result, so basically we are going to index into 1, 0, which is this particular PhD, and then the offset. So inside that you're going to go into 1, 0, 1, 0, 1, 1. So basically this is just another way of viewing it. So either you view it the previous way or this way, it is still going to index into the same component here in the table. So there is another, this is another example. This is just the same Gselect. This is also sometimes called as a GAG predictor. What this means is global history register and a global pattern history table. So this means that there is a PhD which is again shared. There's just one PhD here, which is again shared between different branches, and that's why it's called global. So there is a global history register, a single branch history register. That's why it's called global. And there's a single PhD shared between different branches, and therefore it's called again global PhD. So that's what is called as GAG, uh, global address and global pattern history table. Now, if you look at this, let us say, for example, we have different PCs and different BHRs, as in these two examples. So this is example one and this is example two. But then when you concatenate them, they're resulting into an index into the same entry of the PhD. So this, of course, may not be a good way. Therefore, the more popular and the most commonly used famous predictor is what is called Gshare. So what they figured out is that instead of concatenating the BHR with the PC, we could just XOR it. So we XOR the bits of the BHR and the PC. And in that case, if you try out the same example, you will find that the result of this XOR is going to be indexing into different entries of the PhD. So they figured out that doing an XOR is a much, much better way of indexing into the PhD. So there will be lesser collisions between different branches. And this kind of a predictor is called a Gshare predictor.